For 10 years, the world's best chemists tried to shorten this synthesis. In 2016, it took 24 steps. Then, in April 2026, Mingji Dai's group at Emory University cut it to 7. This is the story of how they did it. 7 steps, 9 CC bonds, 4 quaternary centers, 0 protecting groups. Before we dive into the chemistry, let's answer the most important question. Why should we care about this molecule? Conidiogenone B is a natural product isolated from a deep ocean fungus. It has 2 powerful biological activities. First, it kills MRSA, the bacterium responsible for thousands of hospital deaths every year. Its MIC, minimum inhibitory concentration, is just 8 micrograms per milliliter. That's potent. Second, it's an anti-cancer agent. It shows no micromolar to nanomolar activity against multiple cancer cell lines. And the mechanism is fascinating. That alpha-beta unsaturated ketone I'm showing you is a covalent warhead. It binds to cysteine residues on targeted proteins, forming a permanent bond. This is the same strategy used by some of the most successful cancer drugs on the market today. So, Conidiogenone B isn't just a pretty molecule. It's a potential lead compound for fighting drug-resistant bacteria and cancer. That's why Dai made 296 milligrams of it. Look at what makes it hot. 4 fused rings, 4 all-carbon quaternary centers, and alpha-beta unsaturated ketone, that cyclohexanone right here, sitting on top of a cage-like tricyclic system. Now, ask yourself, where could this come from if we are going to break a bond? Which bond? Here is Dai's key insight. Conidiogenone B with the cyclohexanone A ring comes from an imino intermediate 27, which comes from the imino radical 28, which comes from compound 29. One retrosynthetic cascade, one strategic disconnection. Watch the logic. The ketone becomes an imine. The imine becomes an imino radical. The imino radical comes from 6-axle dig cyclization onto an nitrile, breaking the city bond that forms the vicinal or carbon quaternary center. This is the bond that every previous synthesis struggled to make. Dai's answer, a radical. Compound 29, our beta hydroxynitrile, comes from Ester 30 plus lithium acetonitrile, 1 carbon-carbon bond, 1 functional group manipulation, all in one pot. The Ester is the Trojan horse. It accepts the CH2CN nucleophile, then sodium borohydride reduces the resulting ketone to the alcohol. 3 functional groups perfectly staged for the final MHAT step, metal hydride hydrogen atom transfer. Ester 30 comes from allylic alcohol 32, while a Johnson-Claisen Rearrangement, a shell-like transition state. Compound 31 is the key. The single carbon-6 stereocenter direct facial selectivity, setting 2 new stereocenters at carbon-4 and carbon-5 in 10-to-1 DR. 1 rearrangement, 2 bonds, 2 stereocenters. Allylic alcohol 32, with the B ring now in place. Disconnect back to bicycle 33 plus a simple 4-carbon building block, compound 34. Look at the arrows. The alpha carbon of the ketone attacks an alkyl halide. That's bond number 1. Then the inonate oxygen attacks the aldehyde intramolecularly. That's bond number 2, aldo closure. B ring formed. In the forward direction, compound 34 is too unreactive to use directly. So Dai had a choice. Either use allyl bromide as a surrogate and go through 4 steps of functional group shuffling, or use the Fuchs reagent to install the entire 3-carbon tether and close the ring in one part. He did both. The Fuchs wrote won. Watch the colors. The yellow atoms come from perennial bromide and methyl iodide. The 2 alpha substituents installed in step 1. The green carbons come from the starting cyclopentanone and the perennial methyl. Every color tells a story of where that atom started its journey. Dai starts with the cyclopentanone 35 and runs the Stork-Danheiser alkylation. LDA deprotonates the alpha carbon. The one inaugurates Ester direct ionization there. Alkylate with perennial bromide, then redeprotonate with LDA. Alkylate again with methyl iodide, 1 part. 2 cis bonds. The first all-carbon quaternary center is installed. Compound 38, 75% yield. But there's a problem. The quaternary center is stuck next to the ester, not next to an enome. We need to transpose it. That's where part 2 of Stork-Danheiser come in. Now, the transposition diol reduces the one inaugurates ester at minus 78 to minus 45 degrees Celsius. Acid woke up, hydrolyzes the resulting vinyl ether and dehydrate. Watch the green reagent. The methoxide on the left of the ring has transformed into a cell double bond on the right. The double bond has migrated. Compound 39, 60% yield. Stork-Danheiser complete. Step 3 is the first magic moment. Iron acetylacetate and phenylcyanine. This is the boron reductive olefin cyclization. MHAT generates a carbon radical on the perennial group, which cyclizes onto the enome. The D ring closes. Bicycle 33, 85% yield. 2 rings, 1 quaternary center, 3 steps. Now for the B ring, Dai initially did this in 4 steps. Alylation, cross metastasis with acronym, hydrogenation, aldo condensation, worked but slow. Then he got clever. He used the Fuchs reagent, doubly activated cyclopropane phosphonium salt, as a formal 1,3 dipole, 1 part. The inonate of 33 opens the cyclopropane, and the phosphonium does an intramolecular retic. 2 cis bonds, 1 part, B ring built. Allylic alcohol 32 in a single step from 33. This is why Dai is Dai. Step 6 sets 2 stereocenters in 1 stroke. The Johnson-Claisen trimethyl also propionate pyruvalic acid catalyst 110 degrees Celsius. The allylic alcohol 32 convert to a mixed ketene acetal, which does a 3,3 sigma tropic rearrangement through a shell-like transition state. The existing carbon-6 stereocenter controls carbon-5. The shell geometry controls carbon-4. 70% yield, 10 to 1 DR. Ester 30 is ready. Step 7. Add lithium acetonitrile to the ester. It adds twice, generates a ketone, then sodium borohydride reduces it. You get nitrile 29, and look, they got X3 quality crystals. Every stereocenter conformed. The stage is now set for the most ambitious step in the entire synthesis. Before we can appreciate the final radical cyclization, we need to understand how Dai built compound 29. Because compound 29 isn't random. It's a molecule engineered with purpose. Every functional group on it has a job to do in the final step. So let's slow down and watch how Dai transforms ester 30 into this critical intermediate. The reaction happens in one part, but it's really two transformations. First, we need a nucleophile. Acetonitrile, simple CH3CN, has mildly acidic protons on the methyl group. Why? Because the nitrile group stabilizes the electric charge that forms after deprotonation. Treat acetonitrile with N-butylene at minus 78 degrees Celsius and you generate lithium acetonitrile. A carbanion with lithium as its counterion. This is your nucleophile. Now add this nucleophile to ester 30. The CH2CN carbanion attacks the electrophilic carboxyl carbon. The cell double bond breaks. Those pi electrons move up onto oxygen, giving you a tetrahedral alkoxide intermediate. But this intermediate is unstable. The electrically charged oxygen pushes its electrons back down to reform the cell double bond, expelling methoxide, the methoxide group at the leaving group. What's left? A beta-ketal nitrile. The carboxylate has been transformed into a ketone with a new CH2CN tail attached. Here's where students often get confused. You might remember that esters usually react with two equivalents of alkyl lithium. The ketone formed in the first step gets attacked again to give a tertiary alcohol. So why doesn't that happen here? Because Dai uses just two equivalents at a very low temperature. And more importantly, the beta-ketal nitrile that forms has a very acidic proton between the cell carbonyl and the nitrile group. Its pKa is about 13. The excess lithium CH2CN acts as a base, deprotonating this alpha proton instead of attacking the ketone a second time. You get a stabilized enolate that just sits there, waiting for woke up. This is the key to stopping at the ketone stage. Now we quench with methanol. These protonate the stable enolate, regenerating the neutral beta-ketal nitrile. Then, in the same pot, Dai adds sodium borohydride. Sodium borohydride is a mild, selective reducing agent. It reduces ketones, but it doesn't touch nitriles. Perfect chemoselectivity. The hydride delivers to the carbonyl phase, giving a secondary alcohol. And here is the beautiful part. The substrate is already so rigid and sterically bound that hydride approaches from only one phase, result a 10:1 diastereomer ratio, favoring the isomer we want. After workup, we get compound 29 in 75% yield, a bad hydroxy nitrile which confirmed the stereochemistry by X-ray crystallography. Now, step back and look at compound 29. You see three functional groups, a nitrile, a secondary alcohol, and that exomethylene off to the side. You might think they are incidental features of the synthesis. They are not. Every single one of them has a job in the next step. The nitrile will become the ketone of the Conidiogenone B. The alcohol will become the alkene of the enone. The methionine will become the trigger for radical cyclization in one step. Step 7, the MHAT magic, metal hydride hydrogen to atom transfer. All three of these functional groups will transform and build the entire final ring, the second quaternary center, and the biologically active enone warhead. Here's where conventional synthesis would fail. You have an olefin on one side and a nitrile on the other, separated by enough chain to cyclize into a 6-member ring. You need to form a new cis bond that creates a quaternary center right next to an existing one. Ionic chemistry can do this. Both carbons are too hindered. No polarity handle. Dai first tried iron acetyl acetonate conditions, the same ones that worked for D-ring. They failed. The olefin got reduced, but the radical level found the nitrile. He pivoted, inspired by Mars' Navarine C synthesis. He switched to Shenwei's conditions. Manganese DPM is Shenwei hydrogenation catalyst. Phenylcyanine, TBHP. Now, the manganese hydride delivers its proton atom to the olefin, generating a tertiary carbon radical that attacks the nitrile triple bond. A methylated imine forms. Acidic workup hydrogenizes the imine to a ketone and dehydrates the tertiary alcohol in one part. Conidiogenone B, 45% yield, 296.2 milligrams on scale. 7 steps total. Let's zoom out and look at the whole synthesis in one picture. This is the spatial score, a computational measure of molecular complexity. The x-axis shows each intermediate in order. The y-axis shows how complex the molecule has become. Both roads start at the same place, compound 35. Simple, flat, barely more complex than the solvent it dissolved in. And both roads end at the same place. Conidiogenone B, a complex tetracyclic natural product. Which of these steps blow your mind the most? Let me know down in the comment. But watch the path. The blue line. The first generation road climbs, then plateaus through 3 steps in the middle. 3 steps, while complexity barely increases. Those at the aldo-related steps: alylation, metathesis, hydrogenation, moving atoms around, not building complexity. Now look at the red line, the second generation road. It doesn't plateau. It just keeps climbing. Every step adds a CC bond. Every step builds complexity. And it arrives at Conidiogenone B in just 7 steps, not 10. This is ideality. Visualized. A perfect synthesis looks like a steep straight line. That's what Dai achieved.